Hello, this is Paul from Foresight Tech. In this lecture, we're going to deal with the limit definition. In the last section, 2.1, we discussed two classic problems in the history, right? The first is slope, the second is velocity. And to solve both problems, we need the concept of limit. Okay, more than 300 years ago, Isaac Newton the first time defined this, proposed the definition. So here is what the definition is. So we call the intuitive definition. Okay, keep in mind that when we go into 2.4, we will give a very strict mathematical definition using epsilon and the delta language. Okay, so first, what is the definition? Intuitive definition. Can we look at? You remember the last time when we did was the limit adjusted from the table, right? We have a sequence of a number or the sequence. I'm gonna look at the pattern of the sequence, okay, and the number will close to the sequence will close to a number, so that number we call the limit, right? So it's the same. So can we look at it here? Now we have a notation. This limit f(x) as x approach a is L, right? So this is the mathematical language. The limit equals L. Usually we say the limit of the function f(x) as x approach a and equals L. The limit equals L as the variable x approaches a. Okay. So in the future, LIM is the limit. Okay. How to define? Can you see? If we can make the value of f(x) arbitrarily close to L by taking x sufficiently close to a on either side of a but not equal to a, this is the definition. What does this mean? This means when x gets closer to a, the value of the function f(x) gets closer and closer to L. What does close and close mean? So arbitrarily close, okay? It means f can arbitrarily close to the value L as x arbitrarily close to a. Here is either side. Do you remember when we deal with the snowball questions? And the P is the point, and the Q is another point, right? The point the Q could be on the right side of P or the left side of P. We should be both sides, okay? So that's why we both sides, but not equal A. So we were talking about this later, okay? And another, roughly speaking, and this says the value of f approach L as x approach A, okay? Simply, usually in the future, we usually say this: f approach L as x approaches A, okay, like this. And another notation is f(x) approach L as x approaches A. Okay, approach means get closer and closer to. I hope you get something, and I will have an example to show if we have a graph. What does this mean? Okay, we deal with the function. Now we deal with does not equal to A. What does this mean? Okay. Here, so we find that the limit of x as x approaches a, we never consider x equals a. That's what we just say, right? And the limit when x approaches a, or the limit of f, does not depend on the point at x equals a. What does this mean exactly? Can we see? If we have a function, draw there, and the a is here. Okay, so this function we define the value of f at a, right, which is equals L. Okay, of course, can we look at this? What is the limit of f when x approach a? And then we can see the value. We can see the value of f. Okay, from the left side, the value of the f will get closer to f, and the value of f(x), if x approach a from the right side, can you see, goes down, the height always goes to L. So you can imagine, or let me show you like this. If x from the left side, okay, if the x is here, you can imagine. Okay, so this is how high, and this is how high. Can you see this? When x goes here, and the value of x is this high, when x approach a from the left side, that's the limit. So can you see what is this height? Is this value is the y value. The y value is this. When x gets close to a, see, can you look at it? This is still the y value. The y value will get closer to what? Closer to L. Okay, so finally, so can you see? This is L. When x approach a from the left side, the value of the function f(x) will get higher and higher and higher and closer to L. And also from the right side, can you look at it? Okay, if I say x from here, and gets closer to a from the right side, that's the definition, either side, right? Okay, can you see this? And if x goes to here, okay, so you can see what? Probably I will draw one more. Can you see this? I will draw one more. Here is there, and this is here. Okay, so from the graph you can see this is much higher, right? This gets lower of the value. Can you see this? If we don't look at this, we look at this point and this point. Okay, so the value of the functions gets decrease, right? Gets smaller to what? Smaller, closer to L. That means we look at the right side. Okay, that's the definition of the limit, which means what? And this graph tells us the limit. Okay, this graph tells us what? The limit of f(x) as x approach a, no matter the left or the right, always equals L, right? Can you see? Okay, and these functions we define the value of f at a. See, this is solid. Okay, we look at this graph, and this graph other points are the same except the x equals a. See, when the x equals a, f for a defined is not there, is at here, which means what? This function is totally different from that function. Is different from that function at the point x equals a, right? However, when we look at it, the limit, okay, no matter x approach from the left or approach a from the right, you still have to follow the same. And from here, we also find the limit of f(x) as x approach a still equals L. Can you see? You can imagine, okay, no matter what how high x is here approach a, can you see this? And the height when x approach a, okay, so this height of course approach a, right? No matter is from the right side, the same. If x is here and the x approach a from the right side, the height is still approach to L, which means the limit equals L as x approach a. However, the definition at a is different from that, right? One more. Can you look at this? Even we did not define the value of the f at a. See, this is an empty circle, no define. If we look at it, what the pattern of the value of fx, no matter it's x approach a from the left side or x approach a from the right side, can you see? Still the same. Okay, the value of f still approach L, which means we also get this. Can you see this? No matter which graph, and all have the same, the limit equals L are the same, and the definition at the point x equals a are different. So here we have the definition, okay, and the f a equals L. So here we have the definition f at a lower than L, and the last we don't define, okay. So we don't define f at a, totally no define. However, they have the same limit, which means what? So we look back here. We never consider, if we find the limit, we never consider the point x equals a. All we need is look at the neighbor, okay? Which means all the other points or the other value of x just near a, don't include the a. Okay, so this is very important concept. Does not depend on the value of f at a. We move on. Can you look at we have another definition. Okay, so we just talking about the limits. Then the definition of the limit is no matter x approach a from the no matter from the left side or the right side should be has the same limit, right? Should have the same number. So here, if we don't look at both, or if we look at only one side, we call it one-sided limit. Okay, with the intuitive definition. So can you see what the difference? The limit, so this is what this we call the left hand limit. So only one difference is x approach a from the left side, or we wrote the x approach a, excuse me, and put it to the not exponent. Okay, just put a minus. Minus means approach a from the left side of a. Okay, I will show you example later. The limit, the left hand limit equals L as x approach a. Okay, or we can say as x approach a from the left side, the limit equals L. Okay, it's the same. Can you see what the definition is? Still the same. If we can make the value of f(x) arbitrarily close to L, right? How to close? By taking x sufficiently close to a, or arbitrarily close to a from the left side, on the left side of a, from the left side. Okay, keep in mind that does not equal to a, still the same. Okay, we don't need to consider the value of the function at a. All we need is to look at the neighbor from the left side of a. Let me look at one example here. This is the step function, right? So you know the step function. Here, when t less than 0 or 0, when t greater than 0 or equals to 1, can you see from 0 jump to 1, and the usually we call the step function. Okay, and the point at 0 is defined at 1, not defined at 0. These famous step functions. What is the left limit? What is the left hand limit at x equals 0? So can we look at it's 0? Why? All we need to do is what? So if x is here, we only look at the left side, and or here, or here, or here, whatever, approach 0. Can you see? You take x and they look at f(x). What is f? This is not f, this is h. Or the h x equals 0. Okay. If you put the sequence, it's just this. If you put the sequence, it's just this. Okay. Is put no matter it's 0. Okay. Here is still 0. X go to here is 0. It's all the 0. Can you see? Okay. The sequence is 0, 0, 0, 0. What the pattern? The pattern is still 0, right? So we get the left-handed limit is 0. Okay, we get the left-handed is 0. The same if we look at the right side. Okay, we call it the right-handed limit. So one difference, can you see, is not from the left side, not put the minus, but put plus on the exponent, on the power. Okay, on the power of a, put the plus, and this notation means the right-handed limit, which means what? Which means we only look at x on the right side of a, on the right side of a. Okay, it's one-sided. Can we see example? Still the step function. If this time we look at the right, what's the limit? So x at here, or x at here, or whatever. Can you see this? Okay, x on the right side approach 0. Can you look at what's the value of y? Is 1. This is 1. All the ones. If you put the sequence is 1, the y value is 1, 1, 1, all the 1. So what is the pattern of the limit? Which is 1, right? Okay, if we look at the value of y from the right side of x, all the ones, so the limit is 1 because arbitrary approach 1, right? Or exactly equals 1 this time. This is the one-sided. Can we look at them? If you put these two-sided, okay, and the original limit definition together, so we have this theorem. Okay, do you remember what the definition of limit x approach a? Okay, here is not a minus, not a plus, which means that the definition of a limit. If it is the limit, we have to look at the left and also look at the right, right? So both pattern approach L, we have the limit equals L. Okay, if either one does not equals L, so we don't have the limit equals L. You know, and this result is just the same, the same condition as this, right? The left limit or the right limit equals L. That doesn't make sense because the definition of the limit is the left and the right both approach to L. See, left limit equals L, right limit, right-handed limit, okay, is also equals L. Both then the same. You don't need to prove this, right? Just the definition. We gave example. Can we look at this graph? If we look at the limit as 1, okay, at the not the limit at 1, okay, we look at the limit of f as x approach 1, okay, as x approach 1, no matter it's from the left or from the right. Can you see? Look at one by one. If you look at the limit, you have to look at both sides. So let's look at the left side first. Okay, the left-handed limit equals what? Can you see this? The left-handed limit equals 0.5. Why? Because no matter x approach from the left side, can you see this? If this is x, okay, if I simply take this as x, okay, and this is the value of f at x, right? When x approach 1 from the left side, the value goes down to arbitrarily close to 0.5, right? Okay, this is the left, which means the left-handed limit equals 0.5. The same if we put x on the right side, like I said here. See, the y value, which means the value of f, lower than 0.5. But when x approach 1 from the right side, okay, so the y value will get up and up and up and arbitrarily close to 2.5, which means the right-handed limit also 0.5. Okay, so the theorem tells us the left-handed limit equals the right-handed limit equals 0.5, so the limit equals 0.5. Okay, so this is an important concept. Can we look at another? So we had the basic definition already, okay? Now we look at one more. If we have a functions, okay, so the domain is goes to from negative infinity to positive infinity. So this time we need to define what is infinite limit. What is infinite limit? Not only the domain, okay. So we don't need to specify the domain from negative infinity to positive infinity, okay. So we only do this. Let me draw you a graph. We still define a limit as x approach a. Okay, if let me get this example to you. Do you remember y equals this function? What is function? So this is the reciprocal function. So everyone know what the graph. So what the graph look like. Okay. So if I put, see, it's like this, right? Can you see? It's like this. Okay. So this, if these are the functions, or this gets here gets close to 0. Okay. If we look at this point, if we take any x at here, x approaches 0. What does that mean? So can we look at the height of the function? The height of the function, the value of the function gets up, and the up to where? So this time different is up to positive infinity, right? So the right side, okay, Another, if you look at the left side, so it will approach negative infinity. Okay, so this is the definition we are discussing. Say the limit goes to infinity. Usually we say is this: the limit of f as x approaches a is infinite. Okay, so we just did the reciprocal. When x approaches a from the right side, it goes to positive infinity. Okay. So how to define? Of course, the graph tells us. Okay, the value of f can be made arbitrarily larger. We just see. You can see, okay, it's arbitrarily larger because when x gets closer to 0, no matter how big the number, okay, the function always go beyond that number, which means f(x), the value of f can be made arbitrarily larger. Okay, so how to? By taking x sufficiently close to a. This is one case. Another case, can we look at what that this mean? Negative. Keep in mind that infinity is not a number, it's not a real number, okay? And this exactly means that the limit does not exist. However, it's a divergence to infinity, okay? And another case does not exist, it goes divergent to negative infinity. What does this mean? Simple like this. Still the reciprocal. If we look at the left hand limit of f as x approach 0 from the left side. Okay, approach 0. Okay, x here approach 0 from the left. Can you see? Okay, so the y value is gets bigger and bigger, but the negative bigger, right? Which means what? Which means approach to negative infinity. The value of f approach negative infinity. Okay, or is negative infinity. The limit is negative infinity. Is the same, right? If you can make the value of f arbitrarily larger but negative, okay, by taking x sufficiently close to a. Okay, so this is all the intuitive. Keep in mind, it's intuitive definition. It's not very strict. Okay. However, when we go into section 2.4, we will have epsilon delta language for you. That's very, very strict. One questions. Okay, one more questions here. So how do you find the limit? Okay, if we know the curve or the graph, so can you see this? So how do you find the limit? The function, we don't know because explicit the formula of the function, but we do know the graph. This is good enough. Okay, this is good enough for us to find whatever we need. So one by one. The first, do you remember what is the definition? Negative. Negative is the left-handed limit, which means you only need to look at x from the left side of 2, right? So can we see? Where is the 2? 2 is here. Look at the left hand. Okay, no matter x is here or somewhere, okay, it gets closer to 2. Do you know what is the y value? The y value is exactly finally close to here, right? Can you see? Close. Okay, you finally, if the y value is here, this point is how high is 3, right? So we find it should be 3, which means the first is easy to find is 3. Okay, so let me see. If up here, so a is the left-handed limit. Okay, I just put the number 3. From the left positive 2, the left-handed limit is 3 because all the y value gets closer, arbitrarily closer to 3. So how about this? What does this mean? Plus. Plus means right-handed limit. So all we need to do is look at the right hand. But this time is different, okay? So can you see? If x is here, okay, or here, or somewhere get closer to 2. Can you see? Goes down to what? To this high. What is this high? This is to 1. The right-handed limit is 1, right? The right-handed limit is 1. So for this case B, we know is 1. So now we can answer the question C. How about the C? Okay. What is the limit as x approaches 2? So do you remember the theorems? If the limit exists, we should the left-hand limit equal the right-hand limit equal the same number, right? No, the left-hand limit is 3. The right-hand limit is 1. They are different. Therefore, we can say this does not exist. The limit does not exist. Of course, we need to explain why. Since what? Since the left-handed limit x positive from the left hand does not equal to the limit right-handed limit. Okay, is that the notation fx? That's the reason, right? The left-handed limit does not equal the right-handed limit, therefore the limit does not exist. Can we look at f at 2? Have we defined f at 2? Yes, we define is there. Okay, so he's here, this is solid and this is empty. Okay, so what do we see? F at 2 is 3. Okay, so this is easy to answer. So this is 3, right? F at 2 is 3. Okay, what does this mean? This means the left-handed limit equals the value of the function. See, the left-handed equals, so that's the left-handed is 3 and the value of the function at 3, but the right-handed does not equal to 3. Okay, so 2 more. What is f at 4? Let me see f at 4. Can you see? F at 4 is here, right? This is f at 4. This is empty. Okay, can we say f at 4 equals 4? No, because this is empty. Empty, which means we never define the value of the function at x equals 4. So you can see this. So for E, how do you say no defined, right? You say it's not defined or undefined, and the value of the function or the function does not define at x equals 4, which means 4 is not in the domain. Okay, the last question is, what is the limit? So we're going to get what the limit. Can we see? It's easy to look at it, right? The left-handed limit is positive 4. The right-handed limit is also positive 4. The hand is also 4. I think you can see. Okay, no matter x is from the left, a positive 4, or from the right, a positive 4, the value of the functions always gets closer, absolutely closer to 4. Okay, all we can say is this. How do you say the limit? So now we can say the limit of fx as x positive 4. Okay, so this is the notation. We follow this notation. Should it be equals y value equals 4? What is the reason? So we have to show the reason. Since the left-handed limit, right? So left-handed, we wrote this fx equals the right-handed limit equals how many? Equals 4. Okay, so therefore we know the left-handed equals the right-handed limit, so the limit equals 4. So that's all. Thank you.